Hi, my name is dr. Ahmath. In this video lecture, we are going to discuss about derivatives of vector functions. Previously we defined the vector functions. We say that now we are going to define the curves using so-called vectors, where those vectors are going to point out to the different points along those curves. So it is the type of the function where we are going to have one input, which is going to be the parameter, and it is going to have multiple outputs. So for the 3D, it is going to give you 3 outputs, essentially the coordinates of the point along the curve. So what we want now is we would like to figure out how to apply the tools of calculus, so namely how we can take the derivatives of the vector functions and what are the meanings of the derivatives and how we can integrate the vector functions. So in this lecture we are going to discuss about how we can take the derivatives of the vector functions. So let's choose the point here, and if I would just make a tangent line, I would have a vector which is going to be parallel to the tangent line. That's going to be called as a tangent vector. Well, the definition of the tangent vector is a vector which is parallel to the tangent line at this point to this curve. So parallel to the tangent line. And that's essentially going to be equal to the r prime of t. And you should know that r prime of t, it's also going to be a vector. So we are going to deal with the vectors in 3D. So if you are given a vector function in 3D, it means that it is going to have 3 components, then the derivative of this vector function is also going to be in 3D, and it's also going to have 3 components. Well, the derivatives of the r prime of t is going to be equal to f prime of t, g prime of t, h prime of t, which is natural, right? So that's going to be called as a tangent vector, which is a vector parallel to the tangent line to this curve at this point. Well, it is very important for us to define something which is called a unit tangent vector. It's a vector which is in the same direction of a tangent vector, but its length is going to be equal to 1. So we just obtain this by just dividing the tangent vector into its lengths, so that we're going to have the unit tangent vector. So let's do a couple of calculations on tangent vectors and unit tangent vectors. So let's assume that we're given a vector function using the following curve. We have to find the derivative of this curve. Well, in this example, we have to find the derivative of this function, and in order to find the derivative of the function, we're going to find the derivative of its components. So essentially of the first component, second component, of the third component. So the derivative of the 1 plus t in the cube is going to be equal to the 3t in the square, simply. Derivative of the sine of 2t is also going to be not so difficult. It's going to be cosine of 2t, but I have to multiply this to the 2 because of the chain rule. So I have to multiply this additionally to the derivative of the 2t. Now, in order to take the derivative of the t multiplied to the e in the power of minus t, we'll have to use so-called multiplication rule. So I'm going to take the derivative of the t, which is 1 multiplied to the e in the power of minus t, plus t times the derivative of the e in the power of minus t. It's going to be e in the power of minus t multiplied to the minus 1. So after simplifications and after taking out e in the power of minus t out of the brackets, I'm going to obtain 1 minus t. So the derivative of this vector function is going to be another vector function with the components 3t in the square, e in the power of minus t, 1 minus t, and cosine of 2t multiplied to the t. Well, if you are required to find a tangent vector to this curve, that's exactly it is. So later on, let's assume that we have to find the unit tangent vector at the t is equal to 0. Again, we need r prime of t. R prime of t is equal to the 3t in the square. So e in the power of minus t multiplied to 1 minus t, and 2 times the cosine of 2t, which we have calculated just in the previous exercise. Now we just need to substitute t to be equal to the 0. And find r prime of 0. That's going to be equal to the 0. So e to the power of minus t minus 0 is going to be 1. 1 minus 0 is going to be simply 1. And the cosine of 2t at the t is equal to 0 is going to be simply 1 multiplied to the 2 is going to be 2. 0, 1, and 2. So the unit tangent vector is going to be obtained by finding the tangent vector at this point and dividing this to the length of the tangent vector. Well, that's again going to be a vector, obviously. So 1, 0, 1, and 2 divided to the length of this vector, and it is obtained by summing the squares of its components, 0 in a square plus 1 in a square plus 2 in a square. That's going to be square root of 5. So if I divide the square root of 5 to the component of the vector, it is going to be equal to the 0 simply, 1 divided to the square root of 5, and 2 divided to the square root of 5. Well, that's going to be the unit tangent vector to this curve at the point t is equal to 0. And that's how we are going to do the calculations. Well, let's do one more calculation. So now, let's say you're given a helix, which is going to look like this. And what I have to do is I need to find the equation, parametric equation of the tangent line. Not just the tangent vector, but we have to find the parametric equation of the tangent line. So if you remember, in order to find the vector equation or the parametric equation of the lines, we need two vectors essentially. One vector which points out to one of the points on this line, and the second vector, v, which is parallel to this line. So the vector equation of a line, it's going to be equal to the r is equal to the r0 plus vt, where r0 is the vector on the line and v is the vector which is parallel to this line, where we are already given one point on this line, which is 0, 1, and pi over 2. That's going to be our r0, by the way. So that's going to be our r0. And now what we have to do is we have to find the vector which is parallel to the tangent line. So let's assume that this tangent line, so this point is somewhere, so 0, that's on the x-axis, it's going to be 0. On the y-axis, it's 1. So it's this point is somewhere here, I would say. So this is going to be this point, r0. So it was a component 0, 1, and pi over 2. And there is a tangent line to this curve here. Tangent line. And there is a tangent vector, which we can find by taking the derivative of this curve, which is given like this. So essentially, r of t is given as 2 times the cosine of t, sine of t, and simply t. Our prime of t is going to be our vector, which is going to be parallel to this tangent line, which is simply nothing else as the v from the equation of a line. So this is going to be equal to, so 2 times the cosine of t, it's going to be minus 2 times the sine of t. Derivative of the sine of t, it's going to be simply cosine of t, and derivative of the t, it's going to be 1. Okay, so this point is obtained by when we substitute t to be equal to the pi over 2. Do you know how I know this? Because you see, so z is equal to the t. So if you substitute t to be equal to the pi over 2 into here, you're going to indeed get this result. So x is going to be equal to the 0 because cosine of pi over t is 0. Y is going to be equal to the 1 because sine of pi over t is 1, and z is equal to the pi over t. So I have to also substitute the pi over 2 into here. So the r prime of pi over 2, that's going to be minus 2, 0, and 1. Now I'm ready to substitute this into this black equation and calculate the vector equation of a line, of a tangent line. So it's going to be, so r0, so r of t is going to be r0, which is 0, 1, and pi over 2, plus minus 2, 0, and 1 multiplied to the t. Well, the parametric equation of this line is going to be x is equal to the minus 2t, y is going to be equal to the 1 plus t, or simply 1, sorry. So it's going to be simply 1, and z is going to be equal to the pi over 2 plus the t. So that's going to be the parametric equation of a tangent line to the helix was the following equation at the point t is equal to the pi over 2. Well, again, so the algorithm of finding the tangent line the parametric equation of the tangent line or the vector equation of the tangent line is the following. So you have to figure out, first of all, the point on this tangent line, and second of all, you have to find the tangent vector by taking the derivative of the vector equation, vector function, and evaluate this vector function at your point. So this is what we have done this, and then just substitute this into the vector equation of a line and find its components in order to find the parametric equation of the line. Well, this is what I wanted to discuss with you about the derivatives of the vector functions. We did some exercises, and I hope that you now have more feelings, more understanding about the vector function. Thank you very much.